I've hinted at the link between confidence intervals and hypothesis testing. In this section, we're going to further delve into hypothesis testing, and we'll see an explicit link between confidence interval building and hypothesis testing. So we have a sample of size n from a population with mean mu and variance sigma squared, and as before, we'll let x bar represent the sample mean. If the population is normal, then we know that the sampling mean follows a normal distribution that has the same mean as the original population, mu, but for which the variance is reduced by the sample size, sigma squared divided by n. So the larger the sample is, the tighter the variance of the sampling mean population is. If the population is not normal, what we've also seen is that as long as the sample size is large enough, then the sampling mean follows approximately a normal distribution with the same parameters, mu and sigma squared over n, and that's thanks to the central limit theorem. So for this specific section, we do assume that the population variance is known and that the hypothesis concerns the unknown population mean mu. We are trying to find mu in the original population. And you'll see that this parallels what we've done with confidence intervals, right? We first learned how to build confidence intervals, assuming that we knew the variance of the population from which the random variables were drawn. It's the same idea here. We're going to start with a left-sided test. That's the one I'm going to explain in detail. The other alternatives are also similarly explained. You just need to modify the explanations to take into account which one of the alternatives you are considering. So we want to find what the unknown population mean mu would be. We are testing for the null hypothesis that mu is equal to some candidate value mu naught, mu zero, against the left-sided alternative that the true population mean is in fact smaller than the candidate value mu zero. If we want to evaluate the evidence against the null hypothesis, we compare the sample mean to the candidate value for the population mean mu naught. If the null hypothesis holds, if the true population mean mu was equal to mu naught, then what we've seen is that this quantity here, the standardized quantity according to the central limit theorem, the sample mean x bar minus the candidate mu naught divided by sigma divided by square root of n, that should follow approximately a standard normal distribution. The observed value, x bar minus mu naught divided by sigma divided by square root of n, z naught, we call it the observed value of the z-test statistic. If that observed value is smaller than 0, then you have some evidence to suggest that mu is in fact smaller than the candidate value mu naught. But you would only reject the null hypothesis in favor of the alternative if the evidence is in fact significant. Having some evidence is not enough. How much smaller than 0 does it have to be before you feel comfortable in rejecting the null hypothesis? Right? Because if the null hypothesis was true, this thing should be very close to 0 for the most part. But we know that in the standard normal distribution, there is weight associated to values smaller than 0. So, I mean, it wouldn't be too surprising if Z0 was here, for instance. It might be surprising if Z0 was here, because here there's barely any probability for that score. So it's not sufficient to be smaller than 0. It's going to be related to how far away you are from 0. And how will it be related? Well, it's going to be related through the critical region. So we pick a level of significance, typically 5% or 1%, and we compute the critical value that corresponds to these levels of significance. So if we draw this standard normal, this would be here, the value that makes it so that the area to the right of it is 1 minus alpha. Now this is a one-sided test, and later we'll see two-sided tests where in fact we're interested in the area between the shaded bits being 1 minus alpha. But for the left-sided test, it is only this chunk here. So we'll reject the null hypothesis in favor of the alternative only if the Z0 score that we observe is actually smaller than the critical value of the standard normal at significance level alpha. We've seen that this actually corresponds to a p-value for the test, and that's the probability of observing evidence which would be as extreme or potentially more extreme than the current evidence we have in favor of the alternative H1, assuming that the null hypothesis is true. In other words, it computes the probability that we would observe such an extreme value simply by chance. It might happen even if the null hypothesis is true, it's just we would have to be quite unlucky for it to happen. Extreme cases, even more extreme cases. In this case, as the drawing showed you, that means that we're moving further to the left. So the p-value would be the probability that the standard normal distribution would be smaller than Z0. That's the area underneath the curve from minus infinity to Z0. That is phi at Z0. Importantly here, this Z0, it's the observed value for the Z statistic. It's what you obtain when you actually replace the sample mean by the actual sample mean that you have in your sample. So the decision rule is quite simple. If the p-value is smaller than or equal to the significance level, then you would reject the null hypothesis in favor of the alternative hypothesis. You're saying this is just too unlikely to happen if the null hypothesis was true. It must mean that my true mean, the true mu, is not the mu0, the candidate that I had advanced, that I had claimed was the true one. If the p-value is greater than alpha, then you fail to reject the null hypothesis, which I remind you doesn't mean that you accept the null hypothesis. It just means that you can't reject it. Graphically, this is what it looks like. So if you're doing a left-sided test, if you're testing for the null hypothesis that the true population mean mu is equal to some candidate mu naught against the alternative that it should be smaller than mu naught, well, you're going to first find in the standard normal distribution the critical value that corresponds to an area alpha, area 1 minus alpha. You compute the observed Z statistic, so the observed sample mean minus the candidate divided by the known standard deviation sigma divided by the square root of the sample size, and if that quantity is smaller than the critical value that you found here, then you would reject the null hypothesis in favor of the alternative hypothesis. You're too far from the central regions of the standard normal distribution, which means that this quantity here probably does not follow the standard normal, which means that this is probably not the true population mean. Well, you can do a right-sided test instead of a left-sided test. If you had reasons to believe that the true population mean was in fact larger than the candidate value, and you were pretty certain it couldn't be smaller, then you would instead be looking for scores in this region. At a significance alpha, you find a critical point that guarantees that the non-rejection region has an area of 1 minus alpha under the curve. This area here is alpha, and if your observed Z statistic is greater than the critical value, then you reject the null hypothesis in favor of the alternative hypothesis, which in this case has changed. But it's the same principle as what you had done in the left-sided alternative case. And you can also imagine that you are uncertain whether mu is equal to mu naught or if it should be smaller or larger than mu naught, the candidate, in which case you will consider a two-sided test. Here, the non-rejection region still has an area under the curve of 1 minus alpha, and in order for this to make sense, that means that you are looking for the critical values where the area here would be alpha over 2, your significance level alpha divided by 2. So when you test for the true population mean being equal to the candidate value mu naught, your null hypothesis, against the alternative that it is not equal to mu naught, then you are interested in computing the absolute value of the quantity, and if this absolute value is greater than this critical value, but here note that the level alpha 2 is different, then you would reject the null hypothesis in favor of H1. And we put the absolute value here so that we don't have to say if Z0 is smaller than minus Z alpha 2, or Z0 is larger than the other critical values at alpha 2, then we would reject blah blah. So this expression here covers both cases simultaneously. So what's the procedure? If you want to test for the population mean mu being equal to mu0 is some constant, some claim, you set up the null hypothesis, then you select an alternative hypothesis H1, what it is that you're truly trying to show using the data. And depending on the context, you'll be picking one of three alternatives. Either mu is smaller than mu naught, or mu is not equal to mu naught. One-sided test to the left, one-sided test to the right, a two-sided test. Then you choose a significance level alpha, which I remind you is the probability of making a type 1 error. And typically you would pick an alpha of 0.01 or 0.05. You look at your observed sample, you compute the observed value of the Z statistic, which is obtained by doing the central limit theorem standardization. Sample mean X minus the candidate mu0 divided by sigma, which you know, in this case, this is the assumption we've made, divided by the square root of the sample size. You determine the critical region depending on the type of alternative hypothesis that you have. So either Z0 greater than Z alpha, or Z0 smaller than minus Z alpha, or the absolute value of Z0 being greater than Z alpha over 2. And I remind you, the critical region is also called the rejection region. And the Z alpha is the critical value that will satisfy that the probability of Z being greater than Z alpha is equal to alpha if Z follows a standard normal distribution. It's probably easier for you to remember these drawings. The two-sided case, the right-sided test, the left-sided case. It also doesn't hurt for you to know what these values should be. You'll be seeing them over and over again. It might be useful to know what they are. There's only 4 values to remember. If alpha is at 5%, the critical value Z alpha is at 1.64, 1.65, and the critical value Z alpha over 2 is at 1.96. If alpha is 1%, the Z alpha is 2.33, and the Z alpha divided by 2 is about 2.58. But if you don't remember them, it's not too difficult to go and read them off of the standard normal table. So remember how to do that. Make sure you know how to compute these critical values. And then you compute the associated p-value. If you're looking at a right-sided test, then you're looking for the probability of Z being greater than your observed Z0 score. If it is a left-sided test, then you're looking for the probability of Z being smaller than the Z0 score. And if you are looking for a two-sided test, then it'll be twice the minimum of these probabilities. And your decision rule is simple. If the p-value is smaller than alpha, then you reject the null hypothesis in favor of the alternative. If, on the other hand, it is greater than alpha, you fail to reject the null hypothesis. That's all there is to it. 6 steps. Just follow the steps, and you will be able to do hypothesis testing. Let's look at a first example here. So you manufacture a bunch of components. And in the manufacturing process, they're supposed to get a strength, which would be normally distributed with a mean of 40 units, whatever that unit would be, and a standard deviation of 1.2 units. So we modify this manufacturing process now, and we think that that should lead to an increase in mean strength. Doesn't change the standard deviation. Prior to the increase, this is how the strengths would have been distributed, and now we believe that with the increase, we should see better strength, higher strength, same standard deviation. How do we test for that? How do we test the claim? Well, we'll take 12 components that have been produced using the new process, and we'll look at the strengths that they have. We measure the strengths that they have. So the question that we have then, is there evidence there to suggest that the mean strength is now greater than 40 units. If you just look at the numbers, like this one's greater than 40, this one's smaller but close, greater, greater, smaller but close, greater, smaller but close, greater, just a little bit greater, 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 and just a little bit greater. I am seeing 3 of the 12 measurements being smaller than 40, 9 of them are greater than 40, and if I look at the differences between each of these measurements and the 40 mean, the old mean, I'm seeing that the ones that were below were very close, so very small negative residuals, and the ones that are above tend to have large residuals, and there's more of them. At first glance, it certainly seems as though this process has improved the strength of the components. But that's just like an eyeball test. We want to use true hypothesis testing. So we'll use a significance level of 5% here to see if we can test for that. So what does the outline tell us? We're testing for the null hypothesis that there has been no improvement in the process, that the new strength population mean is still 40 against the alternative, what it is that we think is happening, what we're trying to prove, that it is in fact greater than 40. Now remember, we are trying to prove this before we have observed the data, right? We don't choose on a hypothesis after we've observed the sample. This is something we set for beforehand. Now we select our 12 components, we test them, we recorded the measurement, and we have a sample mean of 41.125. Certainly this is greater than 40. The question is it significantly greater than 40? Well, we need to compute the p-value, right? The p-value will be the probability that the sample mean in general should be greater than this quantity that we have observed here. And then we do the central limit theorem standardization. X bar minus the candidate mu0 divided by sigma over square root of n. Should that be greater than 41.125 minus mu0 divided by sigma over square root of n? We know what mu0 is, it is 40. We know what sigma is, it's 1.2. We know what n is, it's 12. So if the null hypothesis is valid, if the true mean is 40, the probability that the sample mean would be larger than what we've actually observed should be the same as the probability that the standard normal distribution z will be greater than or equal to this quantity, 3.25. That is a pretty large quantity for the standard normal distribution. And in fact, if you look it up, it's about 0.6%. 0.6 is smaller than our alpha of 0.05. And so we would reject the null hypothesis that there has been no improvement in the component strengths in favor of the alternative, that there has been some improvement, and the improvement has a new population mean mu, which is greater than 40. We don't know what the mu is, the true mu is. We just know that it's greater than 40. It is not 40 anymore. All of these are equalities here because the population, the strengths were normally distributed. So we don't have to worry about approximations. Another way to look at this is that if the model of the null hypothesis was true, if the true population mean was indeed 40, then it's quite unlikely that you would observe a sample mean in any sample greater than the one we had observed, if only by chance, right? I mean, there's a 0.6% chance that this is what we would observe by chance. The only possible explanation, if you don't believe that this is happening by chance, only by chance, is that the manufacturing process has had an effect in the claimed direction. Let's look at another example. You have a set of scales, and they work properly if the measurements differ from the true weight by a normally distributed random error term with standard deviation sigma, which is 0.007 grams. What that means is that whenever you measure the same item, say, meant to be a 1 gram gold standard weight, you measure it on each of the scales, and you will get 1 gram plus some noise epsilon. So the measurement that you observe here is always going to look like the true measurement 1 plus some noise epsilon, and the and the noise will vary depending on the scale that you've used. Right, and what we're saying here is that the noise follows a normal distribution with mean 0 and with sigma equal to 0.007. It's conceivable that the error in the measurement will be negative here. You'll get a measurement which is slightly smaller than 1, or it could be positive. But it does so symmetrically, as likely to be negative as it is to be positive, and the standard deviation in this noise is 0.07. Now let's say that our investigators actually suspect that the scale is systematically adding to the weights. So we'll test this hypothesis by making 10 measurements on a gold standard unit, which we know weighs 1.0 grams. It's been tested. You do it 10 times, you get 10 observations, you do the average of these 10 observations, you get a sample mean of 1.0038. It's pretty close to the 1.0. It could, by accident, by chance, presumably be what we observe, but keep in mind here that the noise has a very slight, small standard deviation. Is 1.0038 actually that close to 1.0 if the noise is only meant to be 0.007? Does that measurement here, that average of the 10 measurements, does it provide you evidence that the scale adds to the measurement weights? Well, we can look at this using various significance levels. Mu will be the weight that the scale would record in the absence of random error terms, right? And we're testing for the null hypothesis being that mu is equal to 1.0 against the claimed hypothesis that it actually would be greater than 1.0, that it is systematically adding a little bit more than it should be adding. We compute the sample test statistic, the sample mean minus the H null candidate, divided by 0.007 divided by square root of 10, and that's equal to 1.7167. It's large, but it's not that large. The critical value for this one-sided test, if you look at the 5% level, that's 1.65, which is smaller than the value we've observed here. But the value we've observed is smaller than the critical value at the 1% significance level, 2.33. So you would reject the null hypothesis if you were at the 5% confidence level in favor of the alternative. So at 5% significance, you would actually say that the scale somehow has been tainted. It adds a systematic weight, but at the 1% level, 1% confidence, you would not be able to say that given the evidence that you've collected. So the significance level actually affects how you conclude your tests. There's another possibility here. It could be that what you originally thought was a 1 gram gold standard weight was not actually a 1 gram gold standard weight. But here let's assume that it was indeed a 1 gram gold standard weight. In the previous example, we're gonna assume here that the investigators think there might be some systematic misreading, but they don't know in which direction it is. So does this sample data here provide you evidence that the scale is systematically biased? Again, we'll use significance levels of 5% and 1%. The mean would be the same as in the previous example, 1 gram, against the alternative that it is not equal to 1 gram. The test statistic has not changed, right? It's still the sample mean minus the candidate mu 0 divided by sigma divided by square root of n. That's still 1.7167. But now our test has changed, right? We are interested in computing whether the absolute value of the test statistic is greater than the critical value at alpha over 2 or smaller than the critical value at alpha over 2. This is a two-sided test. For both alpha at 5% and alpha at 1%, the absolute value of the test statistic is smaller than the critical value at alpha over 2, and so you would fail to reject the null hypothesis. If you don't know in which direction there might be a problem, that same data doesn't allow you to reject the null hypothesis, doesn't allow you to accept the alternative hypothesis. How we provide an interpretation for the test statistic depends on the type of alternative hypothesis we've selected. And so it depends on the context. When we let the data speak, we never let it speak unaided. We let it speak in a context that we're given the data. That's an important lesson to remember. Now let's assume that the grades for an average class would be normally distributed with mean 60 and variance 100. In a given class, I pick 9 students. Their average mark is 55. Is that class, the class from which the 9 students come, actually below average? Average, above average? Well, let's say that mu was the true mean of the new class that I'm working with, from which I've picked my 9 students. We're testing for the null hypothesis that the true population mean is also 60%, that the true average of this new class is 60%, against the alternative that is actually below 60%. I'm trying to test if this class is below average. The observed sample test statistic then would be x bar minus mu 0 divided by sigma divided by the square root of n, and I get a minus 1.5. The corresponding p-value, the probability that the sample should be smaller than 55 by chance, assuming that the null hypothesis holds, is the same as the probability that the standard normal variable z would be smaller than minus 1.5. It's a fairly small probability, about 7%. But 7% is still large enough for me to say that this could actually happen by chance. There's not enough evidence here to reject the claim that my class is average. I can't accept that it's below average just on the strength of this evidence, whether I use an alpha level of 5% or 1%. What's happening here is that the standard deviation is large enough and the sample size is small enough that it could just be that when I picked 9 students from my current class, I didn't pick enough of them. Or I happened to be unlucky and I picked, in my group of 9, 5 of them who were very poor and 4 who were average. If I increased my sample, I might see that the sample mean increases. But if I increase the sample and the average mark stays close to 55, then that's probably going to give me enough evidence to be able to reject the null hypothesis that my new class is average. And I'll be able to conclude what I want to show is that it is below average. So the sample size and the standard deviation will actually play a role. Consider this situation here. Same setup as in the previous example, but I'm going to look at 100 students in the new class, not 9. If my class average has not changed, if the class average of my 100 students is still 55, I would expect that there should be some movement in how I decide the test is working out. We're still testing for the null hypothesis that the population is 60 against what I want to show, the alternative that it's actually below 60. But the observed sample test statistic has changed. I'm not dividing here by the square root of 9, I'm dividing by the square root of 100. And that gives me a new z statistic of minus 5. The corresponding p-value, the probability that the sample should be smaller than 55, is now the probability that the standard normal would be smaller than minus 5, and that is substantially smaller as a value than the minus 1.5 here. In fact, it is so small that it is nearly 0. I would then reject the claim that this new class is average, regardless of whether you use an alpha of 0.05 or 0.01. The sample size actually ends up playing a role in the determination of the conclusion of the test. So does the standard deviation, mind you, right? That's another thing you'd be dividing by here. If you follow scientific literature, you will have heard that people are starting to have that there's starting to be some resistance to the use of the p-value as this sacrosanct statistic, sacrosanct approach. Becoming more and more common for analysts, first of all, to do Bayesian analysis, and so we're not talking about the same type of things anymore, but even if they stick with frequentist analysis, to bypass the computation of the p-value and to favor a confidence interval-based approach. If the significance level is given, then you reject the null hypothesis in favor of the alternative hypothesis, in this case a two-sided alternative hypothesis, if and only if the candidate value for the population mean is not in the 100 times 1 minus alpha % confidence interval for mu. And you see here there's no need to compute a p-value. You just verify if the confidence interval for the population mean given the data that you have observed contains your candidate value or if it does not contain it. So here's the claim in an example. A particular type of engine uses 20 gallons of fuel to operate for 1 hour. That's the claim. Not every engine will use 20 gallons of fuel to operate for 1 hour. There'll be some variation. From previous studies, in general, the amount of fuel used per hour is normally distributed with a variance of 25. That's sigma squared, that is known. You take a sample of size n equals 9 from the data, and you obtain a sample mean of 23. So the 9 engines that I've picked actually required 23 gallons of fuel on average to operate for 1 hour. Do you think the manufacturer's claim are reasonable? Is it likely to be true? Well, if the sample is 23, you would expect that some of them would be above 23 and some of them would be below 23. The question is the sample large enough? Is the standard deviation large enough to make us doubt the claim of the manufacturer? We'll use a significance level of 0.05, the 5%. So we're testing here for the null hypothesis that the true mean fuel consumption is 20 gallons against the alternative that it is not equal to 20. The observed sample test statistic would then be the observed sample mean minus the candidate divided by standard deviation divided by the square root of n. If we assume that the null hypothesis holds, that should follow a standard normal distribution. My Z0 quantity is 1.8. If I do a two-sided test with alpha being equal to 0.05, I'm interested in knowing where 1.8 falls. Well, if we have a significance level of 5%, the critical value here would be 1.96 and minus 1.96. And we observed 1.8, close to 1.96, but not in the critical region. It's still in the non-rejection region. And so you would not be able to reject the null hypothesis. If you use a confidence interval approach instead, you will now be able to test for various claims simultaneously. Like here we've just tested for the claim that mu is equal to 20. And we found that we don't have enough evidence to say that this is a false claim. But what if we wanted to also test for 20.5, 21, 22, and so forth? If you know the variance of the underlying population, we know it's 25, that's the assumption we make, you can build an approximate 100% times 1 minus alpha confidence interval for the true population mean. It's simply the sample mean plus or minus z alpha divided by 2 times sigma divided by square root of n. Right? This is how you would build a confidence interval given the parameters of this problem. And that's a 23 plus or minus 1.96 times 5 divided by square root of 9, 19.73 and 26.26. So what this is telling us is that we would not reject the claim for any value which falls in this confidence interval. We wouldn't reject it for mu equals 1974, for 2620, and so forth. So that's sort of a powerful tool